Okay, hello everyone. My name is Ario Hamonangan and I want to present our presentations about parking simulations using ultrasonic sensors. So these projects will discuss the designs of a parking safe distance detection system based on the Arduino microcontroller, as well as the search for theories related to how electronic circuit works and programming using the Arduino. The manufacture of these ultrasonic sensors is a tool that can be used by car drivers to measure the distance between the barrier and the car by using an ultrasonic sensors integrated in the reverse gear of a car. So the ultrasonic sensors is one of the most accurate sensors among the sensors used for measuring distance. The way the ultrasonic sensors works is by reflecting wave. When an object is detected by wave reflections will occur so that the wave is received by the receivers, which makes the sensor high. If the wave is not captured, then the sensor is low. When the sensor detects the object distance, a signal will be sent to produce the desired output. So in this parking simulation experiment, an ultrasonic sensor with an output in the form of a color LED to solve this problem. Drivers of four-wheel vehicles often find it difficult to park their car in narrow locations. So this is the schematic designs for parking simulations. We use the ultrasonic sensors, potentiometers, 3 LED, and this is the 3 resistors. So this is all the components here. Arduino Uno, ESP for the Ario connections and the jumper cables. And this is 3 red LED, green and yellow. The breadboard, potentiometer, sense ultrasonics, and 3 resistors. And this is the NodeMCU schematic designs. So here's the NodeMCU is connected to the Arduino Uno. We connected the Arduino RX and TX with the NodeMCU RX and TX over here. And when the Tinger IO is connected, and this is the output for the IO. We check if it connected or not first. If it connected, and then go to dashboard. In dashboards, we go to this output for the Tinger IO distances. So if the car approaching, the distance will appear from with the Arduino codes.
Okay, so now I will explain about our flowchart of the project or how it works. Basically, the ultrasonic sensor will send waves to to an object, and then after coming back, the sensor will then read the distance between the object and the wall and the sensor, and then depending on the distance, the Arduino will send data to the LEDs to turn on, right? So if the object is within safe distance, it will turn on the green LED. Although this green LED will always be turned on to tell the drivers from far apart that if a parking spot is free. Next, if the object is closing in with the sensor or the wall, right, the yellow LED will turn on. This indicates that the object is near the wall and drivers should park with caution. Next, if the object is super close to the wall, the red LED will turn on. This will tell the drivers to stop parking, to stop their car, because if they keep parking, then the back of the car will hit the wall. So this is the real life image of how it works. So let's just say that this is the car. Okay, so this is the back rear of the car, and this is the wall right here behind the sensor. This is the wall. So if it's close enough, there's still some space between them, between the wall and the car. So the Arduino will then turn on the yellow LED to tell the driver that they should park with caution because they are near the wall. Next, if the object is super close, then the Arduino will turn on the red LED, right? So if we're going to compare, right, the distance, say let's say this is 100 and this is a 50. So within 100 to 50, the only the yellow LED will turn on. But once it's in the 50 radius, then the red LED will turn on. This will tell the drivers to stop parking because anymore and they will hit the wall. So in conclusion, when the tool is turned on, there will be two conditions. Namely when the sensor detects an object in front of it by emitting waves, and then depending on the distance, right, the Arduino will also automatically turn on the LEDs to alert the driver about the decreasing distance. But if the sensor does not detect anything within a radius, then the Arduino won't send a signal to turn on the yellow and red LEDs and keeps turning on the green LED. So the result is that if the distance of the car on wall is more than 30 centimeter, the green light will turn on. This will tell this will also tell drivers from far apart that a, a parking spot is free, and then or the rear of the car is still in safe distance. Then if the distance is nearly 20 centimeters or maybe less, the yellow LED will turn on, indicating that the car is getting close to the wall and a driver should proceed with caution. And then if the distance is close to 10 centimeters, the red light will turn on, which indicates the car must stop and must not continue moving backwards so as not to hit the car bumper against the wall. So that's all for our presentation. We will then next proceed to show our project demonstration in real life. Okay, now I will explain to you about our code. Okay, first I will explain about our code. Then next I will proceed to explain to you about our project, how it works, the components, about how they work together, and other stuff. Okay, so first we will talk about our code, as you can see here. So first this is ultrasonic. It says ultrasonic. So this is basically the pins for the echo pin and the trigger pin. I put it in 6 and 7, LED in LED 1 in 3, LED 2 in 4, LED 3 in 5. This is basically green, red, green, yellow, and red. And then this is also for the ultrasonic, which then will, which is actually not only ultrasonic. Sorry, I'll change just ultrasonic and potentiometer. Right. So there are some things here that also combined with ultrasonic. So that's why I will type as ultrasonic and potentiometer. So this is the setup. Just normal setup: ultrasonic, pin mode, trigger output, pin mode, echo input, the LEDs, everything as an output, serial begin, nothing fancy. And then here comes the void loop. So this is our main code: digital write, trigger high, delay microseconds, which means that every time if the LED is going to lit, or it's going to light up, then the trigger will set it to high, which means that it will activate with a delay of 500 microseconds, and then it can also be low. The value is the value from the value that we will use to to basically set the LED's brightness by using the potentiometer. This is analog, right? LED 1 val divided by 4. This is basically just uh, just basic stuff to light the LED. And then this the duration pulls in echo high. This means that the the input will be high, which means the input to the LED, which will light the LED up. And then the distance equals duration divided by 2 divided by 28.5. This is for the ultrasonic. So after it gets its distance, it will get it by the dividing the duration by 2 and 28.5, and then a serial print and distance. This is for the serial monitor. So this is actually the important part of our code. If distance is less or equal to 60, then LED will be high, right? So this is for the with the green LED. So if the object is still super far away, it will then light the green LED. Let's just ignore this low because it will always be turned on, the green LED, because we will then use it to tell drivers about if there's any free parking spot. So I use else here just to just to fill in the blank. It's really nothing useful about that. And then next, if distance is less or equal to 15, right? Then the yellow LED will be turned on. LED too high, so the LED2 here is yellow. So, but if the distance is not less or equals to 15, that it will not turn on or low. And then if distance is less than or equal to 10, then the LED1 or the red LED will turn on. So of course you can play with the distance here according to your own parking. So say the distance between each car, each car is like 70, then you may want to put here as 60, so that it will keep the it will keep turning on the green LED. So here, this is basically to for the NodeMCU. So we will send the data that we got from the ultrasonic sensor to Thinger IO, which is sent through a NodeMCU which is which have an ESP8266 built in. Okay, so what this does is basically it asks a request from NodeMCU, right? So in order for the NodeMCU to send data to Thinger IO, we want it to first request from the Arduino. Okay, so after asking to the Arduino if it can receive data, it will then delete waste of received data. So basically, it will trim any of the waste. And the request variable that will be sent from the NodeMCU is this. Yes, this is basically the request. So if the NodeMCU request, right, and then the Arduino sends yes, this yes right here, it will then send the data from the Arduino to NodeMCU in order for it to send data further to the Thinger IO. Okay, this is basically the void kirim data here. This is just to send the data from the Arduino to NodeMCU. It's not anything fancy. So basically that's how it works, right? These one are not really important. The important parts are actually this from the void loops. This one, I'll highlight it real quick. Okay, so yeah, this one. Okay, this is the important part. This is like the main code of our project. So I've explained to you about our project. Next, I will explain about how it works in real life. So of course, I'm not going to explain it in in a parking lot, I'm going to explain it using an Arduino and a breadboard. Okay, so first we'll head down here. Okay, so you can see our, let me turn off the virtual background real quick. Okay, there we go. Okay, see. So here, okay, let me put it close. Okay, there we go. You can see here, you can see it clearly here. So this is the Arduino. I'm just going to, so see in my left hand here, this is the Arduino and this is the breadboard. Okay, so you see the light turning on and off because it keeps detecting my hand. Okay, so how it works is that, say that, let me put it, let me just put it right here. Okay, good, perfect. Okay, so let's say that my hand here is a car, the battery of a car. Okay, you can see here that the green LED is already turned on. We can, of course, increase the brightness with the potentiometer, but let's see, you can see how the brightness is turning high and low because I keep turning the potentiometer. Okay, so of course, if we put the potentiometer to 100, every LED will turn on. As you can see, right? And then if if we turn it low, only the green LED will turn on. See, you can see it right here. See, you can see the green LED is turning on super super dim. See right there. Okay. Next, we will test. So let's just say this is my hand is a car, right? So at this distance, it will not turn on the yellow and the red light because, well, it is within a safe distance. But once you can see, once my hand is getting pretty close, you see the orange light turning on. See, now this means that the car is between the car is closing in to the wall, and this is basically a caution for the drivers to park slower so that it may not crash. Next, if I put my hand all the way up here, it will turn on the red LED, right? So this basically means that the car has to stop parking and stop moving backward further in order for them not to crash. So this is basically how it works, right? So you can see that this one right here, this is the ultrasonic sensor. So this two here is the one that emits the waves to the object, and then once it's reflected back, it will then cut the distance, and judging by the distance, the Arduino right here will send data to the LEDs to turn on. So for the LEDs here, as you can see, we're using 3 resistors for each LED, and then we're connecting the jump wires from the LED to pin 3, 4, and 5 to the Arduino. As you can see right here. Okay, great. Next, I will explain about the potentiometer right here. Like, if you can see it clearly, that's the potentiometer right here. Okay, so let's say that a car is parked, right, and we want the brightness to go way up in order for them to see. Let's say that this is at noon when the sun is up, and if the sun is up, then of course the light is not going to be that viewable, right? It's pretty dim. So you can turn on this potentiometer. We can put it to, let's say, a 50, right? So this is 100, this is a 50, and this one's at 0. So 0 and 50, there's really not that much of a difference, but we can control the brightness of the LED by using the potentiometer by turning it on to 100. Say, there we go. See, it looks amazing, isn't it? So basically, that's how our project works. Just really nothing fancy. Some more have already implemented uh, already implemented this system where it helps the driver to know if there's any free parking spot, and it helps the driver to park safer. So yeah, that is for our project. So this is just the main project. I'm not. My friend will show you how we will use it with a NodeMCU, and then we will send it to the Stinger IO in order to monitor the distance. Although to be honest, we don't really need a monitoring for this kind of system because it's uh, it's it's already automatic, right? It doesn't need monitoring from a human unless maybe there's some problem. So that's all from me. My then will next explain about uh, the project with NodeMCU and Stinger IO. He will also explain about the code that we have written. So that's all from me. We will next hear from my friend.
So this is the code for the Tiger IO in the simulation part here. First, we include software serial for the ESP, and then Tinker ESP for the Tinker IO, and then ESP Wi-Fi to get the Wi-Fi connected. And this is the software serial, data serial for the NodeMCU. We use 12 and 13 over here for the RX and TX to connect from Arduino Uno to NodeMCU. And this millis replacement for the delay. So if we use replacement for delay, when we use delay, if the delay is executed, other program will automatically stop. But if we use millis, other programs will still run. And this is the unsigned long previous millis. So is to check when the last time you checking it. And this is the const long interval 3000. So to get everyone to check how long it will take. Then every 3 seconds we'll start checking. And this is the data variable receive, string data keying. And this is the Tinger IO configurations. We use usernames, device ID, device credential, and this is the variable pin LED. And this is the Tinger IO variable. Tinger ESP pin, usernames, device ID, and device credential. And this is for the Wi-Fi configurations, const charge, SSD, and const charge the passwords. And this is the variable per distance value, ready to send to Tinger IO. We use strings distance over here. Then serial begins, then data serials. So data from Arduino Uno that is sent to NodeMCUs will go into the serial data. And this is the pin mode for LED output. And this is for Wi-Fi connections. Wi-Fi begins, SSD, and the passwords. And then checking the connections. While Wi-Fi status not connected, the LED pins will low. But if connected, the LED pins will high. And this is the connect NodeMCU to the Tiger IO. We use sting.add Wi-Fi SSD and passwords. And data to sense is sting my data in the Tiger IO. And this is the sound and out for the output. We use out distance. And this is the millis configs unsigned long, current millis. If current millis minus previous millis, then this is the update for previous millis. And then priorities, read data from Arduino datasense. So MCU will ask for the data first and then read the data. And this is the read serial data. Use string data and then while data serial dot variable. And this is for the delete data space. Here's for delete data space data.trim. And this is for variable values. So this is our code for Singer AU configurations. Okay, that's it for me. Thank you for listening.